How's it?
Alright, you do the intro. Wait, wrong. You do the intro. Welcome to this week's and then say whatever.
I haven't done that for the past like.
I got OBS.
That's how I felt last time. See, I told you I didn't prep.
Do you know how a motor works?
No, don't ask.
Because I spent like fucking 2 hours just trying to understand how a motor works. Man.
Really? Which type? DC?
Or any.
Brushless?
Oh, any. Do you know what back EMF is?
Yes, to some extent.
Oh yeah, okay.
I don't know the physics of it because I don't remember.
What's up, Joe? Oh fuck.
What made that noise? Are you a controls guy? Are you a controls guy?
I'm doing controls homework right now.
Or you have a raw sticker on your laptop?
I'll ask you lots of questions.
No, please do not. The intro is an intro for a reason. I'm kidding. Feel free to ask anything.
6 months, you're good. Yeah, this is good. Yeah. On the average, I think
I'm not using that.
Alright, go.
It'll help you to point it out.
Like you can't see it. Hey guys, this is a slide. Okay, cool. Hey everybody, welcome to another week of the robotics reading group. I'll start off a presentation on introduction to controls and then Steven will be presenting for the rest of time. I don't know why this is in my hand, but we'll see how useful it is. Actually, this could be the robot arm that I explained forward kinematics with, who knows. Okay, so robot arms move using joints, kind of like our shoulders. This is very introduction, by the way, but kind of like our shoulders, elbows, wrists, hands, like that. And they move through joints like the revolute joint, which is essentially rotation. And so the way you'd express that is through joint angles. So just like theta of this joint, this joint, this joint. And then another type of joint that's pretty common is prismatic joints, is having something like linear actuators and just checking the joint offset to determine how much the joint is moving. In most applications though, we care mostly about what's happening at the tool or the gripper at the end of the robot because that's what actually interfaces with the world. And so to describe where things are in space, we use coordinate systems, also known as frames. And there are two main spaces we care about. We care about the joint space, which is more about the joint angles, the joint offsets, like I said, and those values. For example, shoulder angle, wrist angle, elbow angle. And then there's task space, which talks about how the hand or tool is positioned in an orientation way, X, Y, Z rotation as well. And then the question that a lot of controls tries to solve is how do we translate between this joint space and this task space on the left and right. And the two main tools to do this is forward and inverse kinematics. So forward kinematics is if you have a bunch of joint angles, so if I have like some random robot that is positioned in like a random orientation, how can you use the joint angles at those different joints to then determine the position and at the tool or the hand and its orientation as well. So yeah, the input would be having joint values like Q1, Q2, Q3, etc. And then the output would be the end effector pose in space. You also use robot geometry in along with the joint values. So like the length of the links, the type of the joints that you have as well. And then the second tool is inverse kinematics, so it's basically the opposite of that. So if you have a specific pose or position of the hand or end effector, what angles do you need to get to that pose? And so the input here would be the actual position or orientation, and the output would be joint values that achieve that pose. This is a lot more difficult because there are like infinite ways, or sometimes even no ways, or solutions for the robot to get to the position. So for example, like let's say you have this position, there are so many different angles for all of the joints and many different combinations for it to reach that position. Or let's say you want to define something that is very out of reach for the robot in its space, then there would be no solutions at all. And then the other thing that I kind of wanted to give an overview about is how do we control the robot? What are different ways of programming the robot for control? And so 3 of the most common ways is position control, torque control, and force control. So in position control, we're telling the robot where we want the robot to be. So either in joint space or task space. And the controller, what it does is it compares the desired trajectory or position that you want it to be in to the actual measured position. And then it basically generates commands so that it follows that path. This works really well when the robot is moving in free space without having any like contact with any surface or anything. The thing though is that a lot of manipulators are actually driven by actuators that use force or torque to control the motion of the links. And so for torque-driven robots, you need a controller to determine how to get to a desired position based on force or torque. And an algorithm like a position controller is usually needed to control those torques to get desired actions. The reason why this is so difficult is because you're kind of approximating what the robot will be like, or approximating a model of the robot. So you're assuming a lot of things like the masses, the inertia values, the backlash, and this might not be exactly what the ideal or like the actual interpretation of the robot is. So the torque or the position controller really needs to autocorrect when reality doesn't match the model. And then the other thing is having real world disturbances. So let's say somebody pushes the arm of the robot or adds increased payload. How is the position controller robust to that sort of action? And so one of like to make this more ideal, the best way to do this is to have some sort of feedback loop. So you'd have some sort of desired trajectory in joint space that you'd want, and then at each instant you'd actually have sensors on the robot that maybe measure joint velocity or have joint encoders to measure positions, and then there's a controller that determines the error of where is the robot in real time and where does it want to go, and then based on like some sort of like control law, it can take those error functions as well as the positions and come up with some sort of position control feedback loop to use torque to get to the desired position. And then the last thing is force control. So this is like quite complementary to position control. So position control works really well in free space, but what if you have some sort of object that you want to come in contact with? And so for something like this, force control is very useful because let's say you were holding some sort of glass object in your hand and you were like, okay, let's use position control. I want you to move 2 centimeters in an inwards direction to the glass, but that position is not dependent on all to the position. So maybe you press the glass too much and you end up squeezing it and it breaks. So position is not the ideal way to go about this. And so using force control really helps, and a lot of robotic arms have force and torque sensors on them, especially in the wrist, to be able to tell you how, or to be able to control how much force to put on the gripper or the end effector. And in many tasks with robots that come in contact with some sort of rigid surface and actually have to move in free space, you usually have to use some sort of hybrid control. So, and good example of this is like a robot washing a window. You want to know how much force the brush needs to put on the window to clean it, but you also need to have some level of position control to be able to move that force in certain directions. Yeah, I think that's kind of the recap of controls or introduction to it. Steven, it's your turn.
I have a question.
Sure.
At the end of the day, if you look at the lowest level of tracking, everything is basically torque control. Like, if you look at the way a motor works, right, it's like you send current and there's voltage.
Yep.
And there's your frequency to control how often you swap between a pole so that the
right.
actually turns. So everything is built on top of torque control.
Yeah, pretty much. Yeah. Okay, any other questions? Yes, go for it.
What's the next type of control, like up and coming or in the works?
Sorry?
What's like in the future, what do you imagine the next type of control being?
I don't know an answer to that.
Oh.
I feel like, I mean, I think for the most part, like other than maybe IK not being, maybe not the most effective method because like people literally other than for more than 3 joints in space, from what I understand, like people spend their PhDs learning how to do IK for like 6 joints and stuff. And so maybe having some sort of better method to do IK could be something that's next. But yeah, for the most part, I think like most of these methods are quite effective. I did play with Steven's Trosson arm last week, and I tried implementing FK and IK on 3 links, and it was honestly like a very, not easy, but like you can do it with some linear algebra and matrix multiplication. It's not that difficult or like too complex, to be honest. So
You did it with just like only 3 of the motors, and then
well, not for forward kinematics. Basically, I had I have a video, but I can pull it up. But I basically had a deck of cards in a specific position, and I got the robot to be in that specific position. I got the joint angles, and I calculated the forward kinematics to find out the position of the joint effector to see if it lined up with the actual measurements. And then for IK, I just used 3 motors because using more than that is a pain in the ass. And then, yeah, determining what position those 3.
so FK you use all 6 motors, but IK
use 3, yeah.
Okay.
Yeah.
But there's no orientation, I guess. You just did X, Y, Z
4?
for your IK.
IK, yeah.
Okay. Cool.
Cool.
All right, I will do the next part of the presentation. So Shiza gave a good overview of the controls, and now I'm gonna be going over the paper. So let's go over here, Gemto Humanoid. By show of hands, how many of you have read this week's paper? Approximately? Okay. All right. So I will give an overview, seeing as about half of you have not fully read the paper. So first of all, what is the paper about? Shout out to our sponsor real quick, Malaysia and Brackenbot. And okay, what is the paper about? We can watch this video real quick. So essentially it's teaching compliance for humanoids, which is, I think, something really interesting that I haven't really seen around. And so in this video, what you see is we can safely interact with the robot. We can shake its hand, and there's a few other tasks that we will see. You can shake its hand. Say hello. How long is this video? Okay, 2 minutes. I'm gonna do 1.5x speed. Oh, I can't even do 1.5x. All right, you can arm wrestle. And you can also, I guess this is sort of showing the pipeline of what they do, which we'll go in a second. But what you see is that it sort of learns to work around different objects, and it learns this idea of compliance. So based on the size of the object, if it's bigger or smaller, it'll apply different forces, and it can even hug a human, right? And I thought that to be super cool, because this can be very dangerous. If you don't teach your policy compliance, it can actually hurt you, right? Because you can imagine that you just teach it this like hard-coded motion, and it doesn't know how big you are. Like imagine it's a super fat person. It's gonna just kill him, right? So this is why compliance is super important. And before, I guess, I will go into how they actually train this. Is there any questions about high level what the paper is about? Okay, cool. And okay, so let's first talk about compliance. So what is compliance? Compliance is the ability of a robot to adapt to its its behavior based on external forces, right? So when you're hugging this ball, or if you're hugging a human, right, you apply some force on this object, but once you touch it and you apply even more force, there's a resistive force. And so the amount of force you apply will depend based on the amount of resistive force. And so that is what we mean by compliance. You're going to adjust how much force you apply based on the thing that you interact with. And so traditionally, to give some context for those of you who haven't worked as much with humanoids, if you look at like these really cool like Unitree videos, the way they train this is by doing something called like motion tracking. So I actually have a demo real quick that you can run with MJLab. So this is running on my computer right now, and it shows a trained policy of a robot dancing. So what you'll see is that the thing in green was sort of recorded and retargeted for a humanoid. So what someone probably did was either you wear like a mocap suit and you dance, and then you retarget it to a Unitree, or you can just record a video and then extract the human mesh, and then again retarget it to a Unitree, or you can try to teleoperate it. And then what you train through the reinforcement learning process is the actual motor forces the actual torques that you need to apply to each individual motor, which is not available in your data set, because if it was a human, you sort of like don't know, you know the human kinematics movement, so like how it's moving over time, but you don't know what the forces are applied to each individual joint. So that is the thing that you train in RL. But traditionally, what they'll do is the concept of like external forces, they will just treat this as like extra noise. And so anything that makes it deviate from this green path that it's trying to track, it's sort of like trying to go back to this path as fast as possible. So like in this video, what you'll see is like it's doing motion tracking, but then as soon as you push it, it's going to try and get back to its original like motion tracking that it's trying to do. There might be some like implementation details that they're doing slightly differently, but at a high level idea, sort of these policies that are trained are not really compliant, right? They're not made to be interacting with humans. So so the result of this is that they end up being like very rigid, very stiff, right? So if you push it in a certain way, or like if you pull its hand in a certain way, it's going to go back very aggressively to its original motion, because when it was trained, it was treating this as external disturbances. That's bad, gives you bad reward, and it's going to try to go back to its the whatever motion tracking thing that it's trying to track. But you can imagine that for certain tasks, like maybe dancing with a humanoid or hugging, you might actually want to have your policy learn to be more compliant. And so the way they do this, and this took a bit of time, so I'm going to try my best to explain this at a high level. And it builds, I was hoping Shiza was